says. Well, I'll start by telling a little story off topic. Some of you went to the planetarium the other night, saw the presentation about the Voyager. Well, 50 years ago, more or less, I was working at Microwave Semiconductor, and we were making the transistors for the S-band power amplifiers. Intense quality control, ever wafer scanning electron microscope inspection. And the Voyagers had 2 solid-state amplifiers and 2 TWTs. Well, the solid-state amplifiers failed before they got to Mars, and they're still going with TWTs. I hope things have improved in the last 50 years. Okay, anyway, I'm going to try and tell you about Cassegrain antennas. If I can get the right button here. Yes. I think that's OH2. I forgot what it's called, but that's a picture of a nice one. And we'll remember Cassegrain has a subreflector and a feed horn. And of course, it's a very old design. This is the museum in Dresden had this nice Cassegrain telescope, and you can even make them pretty. But the idea is to make it shorter and get the eyepiece or feed where it's convenient. That's one of the advantages. So today we'll talk about the geometry and system design, and then so this is just not theory, examples, results. That's what we want, results. I like the last presentation, take what you got, or both the last two. Take what you got, get it on the air. That's okay. So why Cassegrain antenna? At the higher microwave frequencies, a feed line is a disaster. Even waveguide above 10 gigahertz is lossy. You don't want to run a big piece of waveguide up to the feed. And you can put the equipment at the focus, but most of the dishes I've seen, or many, we don't have all the concrete like W1GHZ that could move a building. If you start adding more equipment at the focus, like a 100-pound TWT, all of a sudden you're way out of balance. And I've been present at least one dish breaking the elevation gear, and it's a big crash. It's very bad for the performance. So we can move the equipment behind the dish and get a better balance. That helps. And mainly, we get the lower noise, higher G over T. Good for EME and radio astronomy. And finally, we can actually illuminate deep dishes, which I don't know about around here, but they seem to be often available in the U.S. that nobody wants to use them. So, higher G over T. All the spillover from the feed horn just goes up into space and contributes very little. With a really deep dish, even at a fairly high angle, you've shielded from the ground by the reflector. So that could be an advantage. Problem is, oops, whatever I hit. Yes. You need a big dish to be effective. The original paper about Cassegrain antennas suggests that you need about 50 wavelengths to be really effective and about a 20 wavelength subreflector before you get to equivalent or better performance than a prime feed. Of course, if you add a few dB of feed line loss to that, it moves the equation pretty quickly. It's loss equals noise sphere equals lots of G over T. Hard part is the hyperbolic subreflector. It used to be very difficult to make. A friend of mine, W1RIL, now a silent key, actually made one on a manual lathe just by cutting diameters for hours. Today, we have CNC machinery, computer numerically controlled, and 3D printing. And the final problem for some is the design is a little more complex than dividing the diameter by the F over D and figuring out where the feed goes. So, next slide. So, we can start out with a simple flat subreflector like these. There's the company over here that makes these little white dishes. Anyway, you put it here, you slide this around and hope it's peaked, usually on too short an antenna range, and you have feed line loss as well, and a very poor feed because it's just an open waveguide. But you make contacts, that's the important part. So, all right, and here KJ1T, who originally Dutch, so some of you might know Henry, was working 148 kilometers on 78 gigahertz, so that's not too bad. Let's see, slide. Okay, so hyperbola. You all remember from geometry 50 years ago that hyperbola is a conic section where you slice through two cones and you get two matching curves. And as you move this sheet, you get many different curvatures. So a parabola is one dimension. All parabolas are the same curve. Hyperbolas have two variables, so there are many possible curves. Okay, but the key point is if you start at one focus and reflect from the other curve, it looks to the RF or light that it came from the second focus, which is going to be the prime focus to the dish. So, slide. And again, feed point at one focus of the one curve and the prime focus to the dish at the focus to the second curve. And this curve went away. And this is the subreflector, reflects off the dish and comes out parallel, just like we want, right? So, if I am talking too fast or not loud enough, yell. Yes. What I just said. Start at one focus, reflect, appears to come from the second focus and from the prime focus, and reflects into a beam, if everything is right. So, what do we need to work out? Feed horn location, where would that be? Well, we decide where it wants to be. Subreflector size, and then we calculate the curve, get the parameters, and then we calculate the points on the curve and put them into the CNC machine or the 3D printer. So, feed form location. Yes, we want the edge illumination to be 10 or 12 dB down. Excuse me. Here and here, so we know the angle of radiation of the feed horn, and if it's wide, we can be close to the subreflector, but if we want it further back, we have to get a bigger subreflector for that same angle, right? So here's our example with a 20 wavelength subreflector and a 50 wavelength dish. That's what we need to be a good performance. And notice we've blocked 40% of the diameter, but 0.4 squared is still 16%. So that's actually not terrible, since we typically estimate with prime focus we lose 15% anyway. So that's also, we can, instead of using the wide angle feed, we can use a narrow one and get a smaller subreflector for the same positioning. Now, I suspect all the 2-meter guys have already left, because nobody has a 50 wavelength reflector 2 meters, except maybe Jan. Okay, and for deep dishes, oops, one of those, we can actually take a feed that's for a reasonably good feed, for a less deep dish, and select it out to the edge, and feed a 0.25 wavelength, 0.25 F over D dish. And efficiently, and it has that advantage that way out here has to be tilted very low before you actually see ground noise. So deep dish actually has an advantage. Feed horn can even be behind the dish if we have a narrow enough feed angle. So, and you'll see where this comes in one of the examples. Okay, so design procedure. Always start with dish F over D and decide where we want the feed horn. And then we work out the feed horn radiation angle. So, not playing with F over D, we actually have those numbers. For any feed that I or next speaker or anyone else has calculated, you have every degree all the way around. And then we calculate the subreflector size, and when it's too big, we iterate until we find a compromise. And then we calculate the parameters and generate the curve. So after you do one by hand, it's not much fun. But I made a little MATLAB routine that does all these and allows for quick iteration until I get where I want it. And since it's a computer, we generate the code right off the program to run the CNC lathe or 3D printer. It's just a matter of getting it in the right format, and away it goes. And I wrote a Perl script to make sketches so you can see how it looks. You know, a bunch of numbers never feels good. And the spreadsheet I made 2004, I talked about Cassegrains, and that's been updated a little. Let's see. So, in that original spreadsheet, I got hung up with space attenuation and that doesn't matter if you know your actual pattern and your actual performance of the feed. So we sheet it on a CNC lathe. You just have it cut all the little diameters all the way out, every tenth of a millimeter of depth, what I thought was probably close enough. And then take one final cut that makes a smooth curve. And all the operator has to do is brush away some chips and take pictures. Of course, the first time you run it, you keep your hand on the red button. Because if you ever run one, the one I use, the motions are hydraulically controlled, and if you get it wrong, it'll go right through the wall. Or at least break a few expensive tools. So, yeah, 2004 spreadsheet, the parameter was equal to fraction of blockage loss. That's a good compromise for large dishes. But for amateur dishes, we'd like to get the subreflector of at least 10 wavelengths, so it actually starts to look like a optical approximation. And as I said, it was compensating for space attenuation, but with good feed simulation, we don't worry about that anymore. So, let's look at some working examples. Most of these are at higher microwave frequencies than anybody but Manfred and Zdenek uses. So think of them as scale models. But to measure performance, I don't know. So we use a long antenna range, find the maximum signal, and then move the subreflector out of the beam. We know the gain of the feed horn. We know the difference. So we can actually measure the dish performance based on the feed organ performance. Anyone have a problem with that? Okay. Okay, so first example is the 122 gigahertz project by our Australian friends, and a little bitty dish, 123 wavelengths in diameter, 15.5 wavelengths subreflector, carefully chosen because that's the size of aluminum rod I had. And the dish is F over D or 0.25. And the feed horn is a large W2 IMU feed, 1.8 wavelength diameter, easy to build with available tooling, with a slight compromise in the flare angle, which gives us this slightly larger rear lobe and makes about a 1% difference in dish efficiency. So I figured that was a reasonable compromise. And there's the dish. 300 millimeters, 120 wavelengths. Machine subreflector right there. Feed horn there. And this model was built by W1GHZ. And notice this dish is nearly optical. It's a very shiny surface. So you can tell just by looking that it's very accurate. It does have a downside, which we'll see soon. There it is. This W2GHZ made a 3D printed mount for the subreflector. They both used subreflector side machine, which are this size pretty easy. And Renee measured roughly 50% efficiency at 122 gigahertz. So for a 30 euro dish, that's probably not bad, right? second one, mine, 48 wavelength diameter, 12 wavelength subreflector. This is a very flat dish, FORD 0.6 at 47 gigahertz. That one. So, as you can see, it's a very narrow beam, and so it reflects. What happened was got a transverter from Michael, made two horns that would just barely fit on it, and went out and made some contacts, but this was the best DX I got with very weak signals, so I figured we needed more. Okay. That's the pattern of the horn. See, very sharp angle. And again, CNC machining, no trouble. And I thought about a waveguide switch, and here's waveguide Spaghetti by Ray, custom bent waveguide. And there's probably some loss in these, I imagine, loss in the switch. So making accurate measurements in waveguide at 47 gigahertz is, I haven't been able to do it successfully yet. So I said, instead of bending the waveguide, why not match it to the transverter spacing and make a 3-port waveguide. Just machine the waveguide right into a block and a rotating plate. Pardon? 5 minutes. We'll get there. Yep, we'll make it. So, before making all the mechanism, I just put it together and tested it. It had about 2 dB loss, and it's heavy and would be hanging right off the feet. So not good. So instead, I said, oops, come on. Let's put the feed behind the dish, put a subreflector out here, and move the TR switch with no loss on a linear bearing. Just switch from transmit to receive by moving it sideways. Now, Manfred, you were trying to figure out how to have a feed for transmit, receive on the same thing. On an offset dish, you could do this, just slide it back and forth. All right. So, feed horns about 23 dBi, the dish adds 18 to 19 dB, which comes out to about 50% efficiency. Again, I'm happy with that performance, knowing that I have that performance, instead of knowing that the dish has a very sharp beam. All dishes have sharp beams, no matter what you put in front of them. All right. So, okay, next one I'm working on 10 gig EME. I have a very nice 1.2 meter dish. And figure 7 wavelength subreflector is about as good as I can, is as big as I can make with the 3D printer I have available. So that's the constraint today. Maybe we can work around it. FORD, and done the numbers, but not tested that yet. Fourth one is 96 wavelength diameter and a 20 wavelength subreflector with another Edmund dish. Again, very shiny, 47 gigahertz. Here's the 4-inch. So that's a 100 millimeter subreflector on the lathe. So, and Renee, W2UG, and I are working on this, and the plan was to compare machine subreflector with 3D printed. Here they are, foil on the 3D printer, metal, remember I said it's very shiny. Renee tested this one with a 3D printed feed horn, pointed it at the sun, and guess what happened? 600 millimeter dish, you're getting about a quarter of a kilowatt of solar energy on the feed. And you can see the profile of the sub-reflector. Final example, pair approached me about making a hyperbolic a sub-reflector for DL0 SHF at 24 or 47 gigs. With that 3-meter dish, I can't imagine pointing that accurately at the moon, but some people are better at mechanics than I am. And so here's the, with the same calculation with the higher gain feed that I used on my dish. But it doesn't make it easier to point. But, oh, let's go back to let's do. So, the same dish, we can use a wider feed and have the feed horn out here, maybe put the equipment right in here instead of having it behind the dish, I don't know. Or we can move it back and shorten the waveguide, whatever works. But the point is, by picking the right feed horn, we can put it anywhere we want. Okay, so, summary. We've demonstrated that we can actually make a Cassegrain with decent performance, has advantages for large dishes, deep dishes. We can reduce or eliminate feed line loss of microwaves, get the switch out of there if you really want. And it is today within amateur fabrication capabilities, which it wasn't until very recently, except for a few people. And I can provide the design procedure tools, and I'll clean up the software and put some comments in it. And I think I'm right on time, right? Okay, so. Yes.
Thank you, Paul. Questions, please.
And there, 47 gigahertz, 148 kilometers, 5.9 SSB.
Questions for Paul?
Can I ask you what aperture efficiency did you achieve at the 4.7 times lambda on 10 gigahertz dish?
What aperture?
The aperture efficiency.
Aperture efficiency.
I haven't
Oh,
done that.
yeah, that's current project. Microphone, please.
Oh, sorry. So the question was, what efficiency have I achieved on the 10 gigahertz example? And the answer is, I'm still building that, so I don't have an answer yet. But.
Good answer. But please, second question. What do you mean about dual optics offset antenna with the Gregorian second reflector?
You have the offset, and then you have the hyperbolic, and you are eliminating the hyperbolic to the offset.
So you're asking about an offset Cassegrain or Gregorian?
Yep.
Just much more complicated geometry and even worse machining. Unless you were going to make 8 of them and you cut a huge sub-reflector and slice them up.
It will be necessary to make a hyperbolic offset. Any other question? Charlie.
You referred briefly to the accuracy of machining. Does the hyperbolic reflector need to have a